Today we'll be covering section 7-1, multiplying monomials. Please make sure to have your book handy, and we are on page 358 today. So today's main idea, we are going to multiply monomials. We are also going to simplify expressions involving powers of monomials. And this is Algebra Standard 2.0 and 10.0, and they are also Casey standards, so it will be on the high school exit exam as well. So at this point you're probably wondering, what is a monomial? It appears in all three of these places right now. Monomials, monomials, monomials. So we are going to start with some vocabulary. Kind of bear with me. There are a lot of new vocabulary terms that we'll be covering today. So, vocabulary. The first of which is a review term, variable. Okay? A variable is defined as a symbol, it could also be a letter, that represents an unknown value. So can you think of some examples of variables? There is one very common one that we use all the time. We use x as a variable. You've also seen us use n quite a bit, okay? So basically all of our letters can be used as variables. However, there are some reserved ones. I'm going to kind of note those on the side, okay? There are some variables that are reserved. Okay? So we'll say these variables are reserved, okay? O, we don't want to use O because it looks exactly like a 0. We also don't want to use S. S tends to look like the number 5 many cases. I is actually reserved. You will be using I in Algebra 2. E is also reserved. It'll be used later on in Algebra 2 and trigonometry. And another one is pi. Pi already has a value that we use, which many of you have seen before, 3.14. Okay? So we tend not to use those variables because they are reserved. Okay? But other than that, you can use all the variables as in all the other letters. You can also use, we can also move on to other letters that you may not have seen before, but you may be seeing in future courses, like there is theta, okay, which is a Greek letter we use as a variable. We also use alpha. We've also used rho. There's other letters that can be used besides the standard letters that you know. You've also seen other variables in use like a box. Okay, in elementary school you probably saw a happy face or a blank. So those are also variables. So variable can be any symbol or a letter that represents an unknown value. Okay. Our next term is constant. A constant is just exactly the opposite of variable. A variable means that it can change. Constants cannot. They remain the same. So a constant is a number that stands on its own. Numbers tend not to change. Constants stay the same. So they're exactly the opposite of a variable, which changes. Okay? So an example would be 2x plus 7. There is a number here that stands on its own. Can you find it? How many of you guessed it was the 2? Did anyone guess it was the 7? In fact, the constant in this expression is the plus 7. That is the constant. Because it stands on its own, there is no variable in there. Okay? Now, the 2 with the 2x is actually our next vocabulary term, okay, which is coefficient. Okay? A coefficient is a number written in front of a variable. Basically, it is multiplied to that variable. So in this case, the 2 in front is called a coefficient, not a constant. Okay? Constant is by itself. Coefficient is in front of the variable. Okay? Moving on, our next vocabulary term is monomial. Okay? Monomial, mono means one, so monomial means one term. It is a product of variables and or constants. So it's exactly one term or one piece. Okay? An example would be 2x. 2x is a monomial. It is a product of a variable x with the number 2, the constant 2. So it is a monomial. Another example could be like 4x squared. X squared means it's x times x. So it's a product of variables and then multiplied by the constant 4. Okay? We could also do fancier other things. Negative 7xy z squared. We can get fancy with that as long as they are all products. They are being multiplied. Okay? And the number itself, 2, we can consider it a monomial because it is a product of constants. Isn't that just 2 times 1 makes 2? So it is also a monomial. Okay? So we're going to do a quick check right now that you kind of understand a little bit more about monomials. What is a monomial and what is not a monomial? Okay? So the question is this a monomial or not? Is x over 2 a monomial? What do you think? Is 2 over x a monomial? What do you think? I will give you a hint. One of these is a monomial, one is not. Okay, go back to the definition itself. It is a product of variables and or constants. Think about x over 2. How else could this be written? Isn't there that invisible 1 in front of the x, the identity 1? So this is in fact 1x over 2. Also, it could be written as 1/2 times x. So if you take a look at this, you'll notice it's 1/2, a constant, that's a number, times x. So this is in fact the monomial. Okay? 2 over x is not a monomial because this means 2 divided by x. It is not a product. So it is not a monomial. Okay? So a quick thing to remember, okay? A fraction can be a monomial as long as the variable is not in the denominator, okay? So you can have a fraction, as in case A, there is a fraction. But notice in case A, the variable is not in the denominator, it's in the numerator. Case B is not a monomial because the variable is in the denominator. So as long as it's not in the denominator, we can consider it a monomial. Okay? So moving on, okay, let's go ahead and start multiplying these monomials now that we have an idea of what they actually look like. Okay? In fact, remember that they're products of variables and or constants. Okay? So example number 1, let's see. I've got 5x squared times 7x to the 4th power. So if we take this and think about exactly what that means, 5x squared is just 5 times x times x. Okay? 7x to the 4th power is 7 times x times x times x times x. Remember that when they're in parentheses, it means that you're going to multiply these two together. So I'm actually multiplying this part with this part. Okay? So what I could do is I can kind of shuffle this around. We have commutative property, which allows us to move around what we are multiplying and not change the outcome. So I can multiply 5 times 7 will give me 35. Now, if I take a look, I have x times x, I have another x, another one, and another one. So I actually have x to the, how many are there? 1, 2, 3, 4, 5, 6, x to the 6th power. Okay, so that would be our solution or our answer here, 35x to the 6th power. Okay, and that's simplified. Okay, let's try another one. Let's say I've got example number 2 here, 6cd to the 5th power times 5d to the 5th, c to the 5th, d to the 2nd. This time the difference is I have 2 variables in this problem. So just like the first one, I could write it out, okay, expand it. So 6cd to the 5th power would be 6 times c times d times d times d times d times d, there are 5 of them, okay, times the next set, which would be 5 times c times c times c times c times c times d times d. Some of you are probably thinking, oh my gosh, I have to write every single one of these out. In fact, you don't, Okay, let's see if we can come up with a shorter way to do this. Okay, we'll finish this one first. 6 times 5, get 30. How many C's do we have here? I've got 1, 2, 3, 4, 5, 6 of them, so C to the 6th power. D, I have 1, 2, 3, 4, 5, 6, 7 of them, so D to the 7th power. And that would be my answer for this one. Now, if you take a look at our two examples, see if we can figure out what the pattern is here, okay? You notice if you have a coefficient, we end up multiplying them together. 6 times 5 is 30. In example 1, I had 5 times 7, it was 35, okay? Now take a look at example 1 and 2 as far as the variables are concerned. In example 1, I have x to the 2nd power, x to the 4th power, and in my answer I have x to the 6th power. Is there a pattern? In example 2, I had c, there's one c here, c to the 5th, I ended up with c to the 6th, d to the 5th, d to the 2nd, I ended up with d to the 7th. Anybody see a pattern here? So what we've noticed is that if you are actually multiplying these together, you can multiply the coefficients, okay, multiply those coefficients, which are the numbers in the front, and then what do we do with the variables and their exponents? You figured it out. We just add the exponents together as long as the base is the same, okay? So multiply the coefficients, add the exponents together for like bases. Okay, that means if they're like variables, exactly the same variable, we can add their exponents together. Okay, so now it's your turn. Go ahead and give these a try. Pause here and go ahead and try these two problems. And we'll check your answer in just a moment. Okay, let's see. How did you do on these? Number 1, did you in fact get 20x to the 5th power? If so, you are correct. And on number 2, did you get negative 6x to the 3rd power, y to the 5th power? If so, you are correct. Okay, so basic rule is we can multiply the coefficients, and then for each of the like variables, we can add the exponents. Okay, one thing to note, if your variable doesn't have a power, you can put in that 1, because that means there's x to the 1 power, there's 1x there. So you can put that 1 in there to help you. Okay, but if you're ever not sure, you say, when in doubt, you can always write it out. Okay, just like I did in the example. You can always write it out and know for sure that you're getting that problem right. Okay? Okay, moving on. We're going to go ahead and have you try these. Okay, so now try these. These are out of your textbook. Okay, on page 361, numbers 4 and 5, and that we'll check in class tomorrow. Okay, this is the last part now. Let's try power of products. Okay, so this is the next level of problem. Okay, example number 3. What happens if I have something to a power? Okay, if it's already to a power, to another power. Okay, so let's take a look at what this really means. This means I have x to the 3rd power, and I have 2 of them. So it's like saying x to the 3rd power times another x to the 3rd power. Well, think about what we just did. We said that x to the 3rd power, there are 3 x's. X to the 3rd power, there are 3 x's. And we're multiplying both of these. So how many x's are there? This comes out to 6, x to the 6th power. Okay? And then if you take a look at the next example, okay, take a look at our next example. You've got 4a to the 2nd power, b to the 3rd power, this whole quantity to the 2nd power. So think about what it means. It means there's 2 sets of them. 4a to the 2nd, b to the 3rd, 4a to the 2nd, b to the 3rd. Got 2 of them, so I could do exactly what I did earlier. 4 times 4 gives me 16. Now, like variables, I can add their powers. A to the 4. B, there's third power. That makes 3 plus 3 is 6. So that would be my answer. Okay? Now, if you take a look, there is a pattern to these. Okay? You notice that if it's a second power, what we can do, okay, we can do this. I'll show you a little shortcut for this. Okay, and again, keep in mind, if you're really not sure about using this rule, you can always write it out. Okay, it's like saying I have each of these parts 2 times. Okay, I have this 4 twice, so I have 2 of these. Okay, I have a to the second, I have 2 of these, and I have b to the third, I have 2 of these. So when you take a power to a power, okay, what's actually happening is this. I take my coefficient, squared is 16. A to the second, if you have 2 of them, you've got a to the second and another a to the second, you've got a to the fourth. B to the third, you have another b to the third, you get b to the sixth. Notice what's happening with these numbers. 3, 2, and then you get 6. You're multiplying these, okay? The powers get multiplied together, okay? So if you're taking this to a power, you end up multiplying the powers, okay? So go ahead and give these a try and see how you do on these, okay? So pause here, try these. Okay, let's see. Remember, you could do this either way. You could write it out if you're not sure, or you could just follow that pattern that we just found out, which is just multiply the powers, okay? So if I follow my pattern and just say multiply my powers, I'll get y to the fourth power to the third. I multiply my powers. So y to the fourth to the third would be y to the 12th power, okay? And that would be correct. And then if I have 9, c to the third, d to the fourth to the second, I can do the same. Multiply my powers times 2. And then remember, I have 2 of these as well. Okay? So 9 to the second power is 81. C to the third to the second power, multiply those powers, is c to the 6. D to the fourth to the second power, 4 times 2 gives me 8. And that would be your answer for this one. Okay? So very quickly to summarize, if you're doing a power to a power, what do we end up doing? We end up multiplying, okay? So a power to a power, okay? You are going to multiply the exponents, okay? But remember, be careful on this one. You must still take the coefficient gets raised to that power. So be careful. So what I'm talking about as far as this is, when we did, for example, this problem here, 9 to the second, remember it's 9 to the second power. You don't multiply that. It's not 9 times 2, it's 9 to the second power to get 81. Okay, so be careful that you don't fall into that. Okay, so that could be a rule. If not, remember what our other rule is. When in doubt, what do? If you're ever not sure, you can always write it out. Okay, keep in mind, when in doubt, you still write it out. Okay? Okay, now last piece. Okay, very last piece. Okay, I'm going to have you go ahead and try this to bring in tomorrow. Okay, page 361, problems 8 and 9. Okay, and now the very last thing, how do we use all this? Okay, there is a link to geometry. Okay, there is a link. We do apply this when we take a look at different shapes. Okay, so here's a quick example. Express the area of each of these shapes as a monomial. Okay, so just to refresh your memory, if you need to, you can look, okay, at the inside back cover, Okay, inside back cover of your textbook. Okay, inside back cover of your textbook. And there is a table of all your area formulas. Okay? Okay? Inside back cover. Take a look, take a peek now. There is a table of formulas if you should have forgotten any of your formulas. Okay? Is it there? Okay, so we're going to go ahead and find the area of a triangle. Can you find that formula right now? Okay. Here is a triangle. Okay. I've got a base of 6w squared, and I have a height of 4w. What is the formula for that area of your triangle? You found it? 1/2 base times height. Okay, so our base is 6w squared. I'm going to replace that in for base, 6w squared. Our height is 4w. Now let's see if we can multiply this together. Okay. Well, you can do some canceling. Like this 2 can cancel out with that 6, absolutely. So I get a 3. And then I end up with 3 times 4 is 12. W squared times a w is w to the 3rd power. So the area of this triangle would equal 12w to the 3rd power, 12w cubed. Okay? Take a look at this shape. Anybody recognize this one? It is a circle. So quickly glance, what is the formula for a circle? Area of a circle is pi r squared. So if you take a look at that, what is the radius of our circle? Our radius is 5x to the 3rd power. So this is pi times 5x to the 3rd power. So to complete this one, we're going to actually take all of this and square it. Okay? So that's 5 squared. Then it's x to the 3rd squared. Okay? So 5 squared is 25. X to the 3rd to the 2nd power is x to the 6th. And I have a pi. And what we're going to do is leave our answers in terms of pi. So we're going to leave that pi right in our answer. We'll just put it in right at the end. So our answer will come out being 25 x to the 6th with a pi. Okay, and that would be your answer for that one. Okay, okay, last set for you to try. Okay, try these on page 361, problems 10 and 11. Okay, bring your 6 problems to class tomorrow and we'll check and see how you did. Okay, see you tomorrow.